Hey everybody, today we'll do another video and it's going to be another Laplace transform inverse type. So it's going to be inverse Laplace transform. So the inverse Laplace transform. I believe I already done the definition of the inverse Laplace transform, but it's basically the inverse Laplace transform says that it's just a given a function of given, right? So given, given a function, or of given a function capital F of S, and that there is a function there is a function f of t, right? A small f of t, right? So basically, that is continuous, that is continuous right? That is continuous on the interval of zero to infinity, right? So basically, you cannot go past zero on this side, but you can go to infinity on that side. But it has to have some parameters on it. It cannot just be any number. So I will touch on that a little bit, but not too much. So it says that the Laplace transform of, so the formula is the following. So the Laplace transform of, right, inverse of capital F of S, like that, is equal to f of t. In other words, you going back to find the original function, right? The Laplace transform is given. Now you're looking for the time for the time domain function. So you're going from the Laplace transform, you're going from Laplace domain to the time domain. And so it says that then we say that f, then we say that a small f of t is the Laplace transform is the Laplace is the Laplace transform okay. So basically what it's saying is, so is the inverse is the inverse yeah, so is the inverse of f of so the inverse, so the small f of t, that's what I'm saying. So basically exactly what I'm saying, I think the book explains it better, because technically you given f of s, then you find f of t. So f of t is the inverse of f of s. Right here, right? So that's what it said. So and employ the notation of and employ the notation of a small f, right, is equal to the Laplace inverse of f, big F inside. So basically that's the definition. So and interestingly enough, if you know, but again, the main goal right here is to have this these parameters. Well, technically this infinity doesn't tell us too much. We have to have a function that will converge, right, at this, because you go to infinity, nobody counts to infinity, right? So basically just God, but unfortunately we cannot do that. So, but if we start at 0, a function at 0, right, and if you go back to, right, so any number to the 0 power is 1, right, and then e to the 0, right, and so forth and so forth, the exponential type, right, the first number, even though the base of that number is 2.71, right, but to the 0 power it still is equal to 1. So it doesn't matter, right? So you're starting at the base, e to the 0 power, so this e represents that, but that number to the 0 power is equal to 1. So start at the base. So that converges. Once that converges, that means that I will have an exponential that goes either like this, right? Or an exponential that goes like this, right? But I cannot have something like goes directly spiking up, right? So that is if the value goes to infinity right here, then there is no point. There is no point to do calculation. In something that it goes to infinity, and we see this a lot of in cases of engineering, when you have a short circuit. When you have a short circuit, you have a spike in current, and that's why you want to limit that, because you don't want the current going to infinity, because that creates problems. And so, but that's one of the things that really, and matter of fact, there's other functions that, define that, there's a delta function, but again, the main thing is to understand this concept. So that is the definition for the inverse Laplace. The inverse Laplace. So now let's, you can read this, the main thing right here, you can read this online or maybe in your textbook, and the main thing is to learn how to do problems. So let's do a problem real quick. So let's do a problem that, the problem is, so the problem is like this. So the problem that we're doing is this. So it's 4. So it's s plus 4 over s squared times s plus 5, right? That is the problem. And the problem says find the inverse Laplace of this, right? So given that this is equal to big F of s, so we're trying to find the inverse of that, right? So we're trying to find the inverse of this, which is inverse of that, right? Which is s plus 4 over s squared times s plus 5, right? Inverse. So this is the Laplace. We're trying to find the inverse, right? So the question is, based on, there is a few methods that we can actually use, but we will just focus on one. So we will just focus on one. So it is going to be the method that we will use is partial fraction. Partial fractions decomposition. So that's the method, right? So okay, so let's get it started. So first of all, we need to identify the problem. And when you do a problem like this, it's a good thing to analyze the problem, right? So first of all, what we have? On the top, I have a regular linear function, right? What is a linear function? A linear function is something that has a slope. Well, technically, that's like a linear in the form of y equal mx plus b, right? On the top, right? Why? Because it's linear. I don't have an exponential. I don't have nothing at the top, so it's a linear. On the bottom, however, I have an exponential. Over here, I have like a parabola, right? So right here, I have a line like this, right? On the numerator, I have a line that maybe goes like that, right? It's a slope, maybe intercept, has intercept of 4, right? Maybe it goes like this. So it goes upward. So it goes 1, 2, 3, 4. Maybe it goes like this, right? Maybe it goes closer to the 4, right? So that is the top. It just goes to infinity like that, right? But this represents this. This right here, if you think about it, I have a parabola. The parabola is multiplying this linear function inside, but at least this linear function has been factored out, which means that over here I have a cube. I have a cube function. Why? because when you distribute that guy inside, it gives you a cube, right? So right here I might have something like this. Right here, I might have something that look like that, right? Right. So maybe I have some type of cube function, right? Maybe I have something like that, right? Maybe I got something like that in the bottom. Don't know. And I don't care too much. What I care is to analyze first, what do I have at first? So I can actually start doing the problem. So I analyze that at the bottom I have some, in the top I got some linear function, at the bottom I got some cubic function, right? At the end, who cares? What you want to care is about how you solve, what method you approach, how you approach this problem. So you know that at the bottom, you multiply that across, you will have a cube, which means that you will have 3 variables, right? That's the most important thing. Okay, so we're trying to find the inverse of this, right? So now, how we go by this? So what we do is the following. So let's say that we do this, right? So we do s plus 4 on the top, right? In the bottom I got this, right? And in the bottom I got s squared, and then times s plus 5, right? Now I want it, make it a partial fraction. I did a partial fraction already, so which means that we're looking for a, right? At least we're looking for 3 right here. So we have s cubed, so that means that we'll have a plus b plus c over something at the bottom. On the bottom we'll have it over something, right? I don't know yet, but identifying the problem I can actually see, right? So right here, what we do, if we have a square in the bottom, that is a square is multiplying another one like that, what we do is that we add another s, right? So we add another s right here, because we have a cube, we have another s right here. So how we do that? So we do a, right? It's going to be over s, right? Plus b, right? What is b? B is the next term. B over s squared plus c over s plus 5, right? Okay, so now looks pretty not too bad, right? Let me give me a little space right here. Give myself a little space. Plus b times s squared plus c times s plus 5. Okay. Now, right here is the most important part that you need to pay attention in this. So what I'm trying to find, right? I'm trying to get rid of this and solve for a, b, and c. But in order to do this, I have to get rid of this denominator, right? So how do I do that? Well, in this side, I multiply by this denominator, right? Which is s squared times s plus 5, right? And then right here, I multiply by s squared, right? Times s plus 5. And over here, the same, s squared times s plus 5. And over here, s squared times s plus 5. Now that I have this, so I cancel, I get rid of this, That's gone. If I have a marker that works better. So that's gone, right? That guy is gone. Right? And then you do this. This right here, you can see that this one cancel with one of this. One. So still have an S on top. Right here. Cancel one, I keep the other one. Let me just write it right here because it's confusing right here. Right? So now this one cancels with that one. Right? And last but not least, this one and that one also cancels out. Okay. Now it's time to clean it up. How do I clean up? Well, that guy stay the same over here, so S plus 4, right? Right here, I need to consider those, right? So I need to multiply, and remember, I'm multiplying the A2, so I write A times S plus 5, right? Plus B, right? So now B is multiplying that guy, so B times S plus 5 and right, B times S plus 5 plus C times that guy plus C times S squared. Okay, so now that I have this, I can actually start doing some solving the problem, right? So how do I do that? Well, I gotta distribute that guy inside. This gotta be distributed, that guy gotta be distributed. This is easy, I don't have to do too much. So S plus 4 equal to A times S squared, that times this S squared, plus 5S, right? Plus B S plus 5B, right? Plus C S squared. Okay. Now I have to multiply this, I have to distribute that A inside, so S plus 4 equal to A S squared plus 5AS plus BS plus 5B plus CS squared. Okay, so now that I have that, I can actually start doing some analytical, you can say, measuring up, right? Measuring up what I have in the left and what I have in the right. In the left, I don't have an exponential, but I have a constant, right? And I also have a linear slope. Think about the slope of 1, right? So you have the slope of 1 in front of that guy. Think about the slope of 1 at that S. Okay? So now, what do? First of all, I need to start thinking about what over here is being a square and what is being linear, right? What is being a square, what is being to the power of 1, and what is being to the power of, technically power of 0, because this is a 0 power right here, right? The constant. So I have this, right? So now what I do is the following. So you can actually do this like this. So you say that the S squared, I don't have anything, right? So how many I have an A and C, right, squared. So I said A S squared plus C S squared equals 0, right? Now, you can actually factor out the s and say as plus c, factoring out the s squared is equal to 0. So, and you divide by s and by s squared on both sides, and you say that a plus c is equal to 0, right? Right? Do you agree with me? Now, a plus c is equal to 0. That is the first equation. What is the next one? The next one, I have to look at something. I have an s and I have an s over here, right? So how do I do that? So I say, okay, so I say I have an s over here and I have another s over here. So I have a, so 5as plus bs plus bs is equal to what? Is equal to this one, to s. Is equal to s, right? So now the same thing. So I say 5as plus. Okay, so factoring out, again, factoring out this, and I have s is equal to s, right? Now I am dividing by s on both sides, right? And then that cancels, right? And that cancels. And I said 5a plus b is equal to 1. So that's the next equation, right? So now, once I have that, what do I have left? So this is gone. This is gone. This is gone. That one is gone. I just need this. So I have, let me write right here. So I have what? So this 4, this 5b is equal to this constant. See that? Because I have a constant. So I already took care of the 0 that we didn't have. I already took care of this. Now I gotta do this, right? So now I gotta do this. So how do I do that? All right. So I said 5b is equal to 4, right? So what are the three equations? The three equations are the following. So a plus c equals 0, right? That's 1. 2 is 5a, 5a plus b is equal to 1, and 5b is equal to 4, right? So I have 3 equations, but I only have 2 unknowns. Okay, so you can say, okay, I have a advantage and disadvantage here. Why? Because I cannot use the process of elimination because I don't have a and b in this one. But I can use the process of substitution, solve for this one, and then substitute, right? So let me do that. Okay, so first of all, let me solve for b first, right? So I got 5b is equal to 4, right? Divided by 5 on both sides, and I get that b is equal to 4/5. All right. So now that is one of them. Now in this equation, right? So you can name this 1, 2, and 3. So 3, I already got it. 2, I need to find a because I have the value of b. I can find a, right? So now, how do I do this? So I substitute the value of b for this, and I get a 5a plus 4 over 5 is equal to 1. Now you can do both, you can do a couple different ways this problem. You can subtract this, bring it over here, and then find a common denominator and flip this and do that, right? Bring it over here, add over here, or subtract, whatever you have to do. And then divide by that, you will get the answer. Or you can get the answer like this. So right now, notice that I have the denominator right here is 5, right? So I can multiply by 5 across, and I get 5 times 5a, right? Over 5 plus 4 over 5 equal what? Is equal to 1 times 5 and then over 5, right? So when I do that, what's going to happen? So on the top I get 25a over 5 plus 4 over 5 is equal to 5 over 5. See that? Now once I get it like this, all I gotta do is go like this, whoop, gone, right? So now what do I have? I have just a linear equation, which is 25a plus 4 is equal to 1. Subtract 4 to the other side, and I get 25a is equal to 1 minus 4. No. It's that was 5. It is 5, right? Which is equal to 1, right? In this case, so it's 1. And this side, so then I got 25a is equal to 1, right? Divide that guy by 25. Divide by 25 on both sides. That is gone. And I get that a is equal to 1 over 1/25. So a is 1/25, right? So if a is 1/25, then I can use, and I already have right here a is 1/25. So now I can actually substitute that a right here and solve for c, right, on equation 1. Okay, so let me do that. So a plus c is equal to 0, right? Now a is 1 over 25, right? Plus c is equal to 0. Move this to the other side, right? Move this 1/25 to the other side, right? And I don't have to do it. I mean, you can do that, but I am subtracting this to the other side, which is 1 over 25. 1 over 25, and these guys go away, and I got a c is equal to negative 1/25. So now I got all the values, right? I got all the coefficients, a, b, and c. Now is the time when we have to use the table to find the inverse. And unfortunately, we still have to use that table. But once you get it to this point, you get it done. It's that pretty much straightforward. So okay, so the table that we use the following. So the table is the following. So the table says that, I'm going to go ahead probably write maybe 1 or 2. So, okay, so the Laplace transform of f of t. So the function of f of t, right? Function f of t, and then the Laplace, and then Laplace on the other side. So, and the Laplace is big F of S is equal to Laplace so the big F of the small f of t, which is this one, is equal to f of s with the Laplace of, on the other side of f and then like that. Okay, so what am I saying? So technically now the first one, the function given is 1. The next one is 1 over s. So in this case it would be 1 over s. When this is 1, this is 1 over s. When it's like this, e to the at, then the other side is 1 over s minus 1 minus a. When, okay, so now it over here is not all of them in this table, that is small. So right here there is another one that says t to the n power, t to the n power is equal to n factorial is equal to n factorial is equal to n factorial over n, so over n factorial, so over s to the n, so it's s to the n plus 1. So okay, so now we're dealing with this table, right? So we need to take a look at, so and the other one that I know of is t. When it's t like this, right here is s squared, right? So 1 over s squared, I'm sorry. 1 over s squared. So when it's t, right, it's 1 over s. But when it's t to the n, then we get this factorial. Total different things. When this is a to the at, then we get this, right? So basically this is the Laplace already. If we can, we use the table to find the Laplace, or you can find the inverse. Because this was given to us, now we're going back to this, right? This is the Laplace domain, this is the time domain, okay? So, with that being said, let me write the value so we can actually use this table real quick. So, we say that A is equal to 1/25, B is equal to 3 is equal to 4 over 5, and C is equal to -1/25. Okay, so with that, let me just erase this, and so we can actually get the final answer. Okay, so in the first one, we need first to find, right? So So A was over S, isn't it? And B plus B was S squared, isn't it? Plus C was S over S plus 5. That was the original problem was. How we set it up. Now, I need to put these values, these ones, like this on the top of this, right? So the first one is going to be 1/25 over S plus 4/5 plus 4 plus 4/5 over what? Over S squared. And unfortunately this look like this. Right? That's an S, this is S, this is a 5. So okay. And then minus 1 over 1/25 over what? Over what? So now we're dealing with we're dealing with this guy, right? So, but remember, so we're dealing with this, right? But representing that, I am not. So S plus 5. Now, think about this. Let's think about this for a moment. Remember that these guys, they have a coefficient, they have a 1 at the top. Each one of them has a 1. That has a 1, that has a 1, and this is a 1. So basically, there is a 1 at the top over here. And every single one of them. And every single one of them. So the rule said that if I have a number at the top, I can bring this in front, right? It's called linearity. Linearity. The linearity tells me that I can bring that coefficient to the front, right? So 1/25, right? And then what is going on right here? So 1/25. And so you know that this has two different things. So this one is also some books and some answers are represented as U of t. This one right here. So this one is get 1/25, but it's something, right? So you can say, U of t. Why not? So times U of t. That one. Plus. Bring that to the front, right? Bring this one to the front. So bring this one to the front, right? So, but that, what was this? So that this one, this part right here, that one, this one is that one, this one is this one. See that? So this one is this one. So therefore, what I can do, and what is the inverse of that? The inverse of that is just t. So I can actually replace that, bring that to the front, and put my t over here instead, right? Replace that with t, put that in front, so I can put 4/5, right? And that multiplying that t, right? Which is this part right here, right? Then I got minus, right? And then I bring that to the front, right? I bring that to the front. When I bring that to the front, this becomes a minus. And I say minus 1/25. Now, what is the next? This one, right? But what is represented by that? That one, right? So now I have to find the number. Remember that this is a negative. But but the number that was inside there was a positive. So basically I am replacing the a and keeping the sign, and that sign will be attached to whatever number goes on top over here. So it's going to be e, right? E to the whatever number is the constant at the bottom. What is the constant at the bottom of this? Is 5, but I have a negative sign in front, so which means that it's going to be negative 5t. Why? Because originally it's given like this, and it was positive. It was positive. Because it was positive, that when I bring that to the top like this, is negative. It becomes a negative, right? And this is the whole idea of this. So basically, what happened? Remember that we say that it's going to from zero, and then to infinity, right? 0 to infinity. If I plug in, this is a decreasing function already. That's what I said. You have to have parameters in the function. If I plot infinity over here, it's going to drop to 0 immediately. Why? Because that exponent is negative. But if it was positive, this goes to infinity. And that's not good. But because it's negative, if I put like maybe a million over there, it's going to drop to 0 immediately. Probably not. It probably doesn't need a million, but maybe 1,000. It will just drop to 0, or closer to 0. Or closer to 0, I will say. But it's going to eventually It's going to go to 0. It's going to be a decreasing exponential, right? And we use that a lot in capacitors, and so okay. But anyway, so now let me just simplify this. So u of t over 25 plus 4t over 5 minus 1 minus, you can put it like this. You can just bring this to the front and put 20, e to the 5th negative 50 over 25. Okay, so and that will be the answer for that. And that is the inverse Laplace transform of that. So the inverse Laplace transform of this. So what do we have? We had this, right? So we had s plus 4 over s squared over s squared s plus 5. And once we find the inverse Laplace of that, this is the final answer. This is the Laplace domain. This is the time domain. Thank you for watching, and I'll see you in the next video.